Good day. Today we will discuss the last part of our lesson 1 and we are going to tackle about electric fields. Let us first discuss the concept of the shark and the sixth sense. So sharks have the ability to locate prey such as flounder and other bottom-dwelling fish that are completely hidden beneath the sand at the bottom of the ocean. They do this by sensing the weak electric fields produced by muscle contraction in their prey. Sharks derive their sensitivity to electric fields, and this is considered as their sixth sense, from their jelly-filled canals in their bodies. These canals end in pores, as you can see in this photograph, and the electric field is as weak as 5 times 10 to the negative 7, and which causes charge flow within the canals and triggers a signal in the shark's nervous system. And because the shark has canals with different orientations, it can measure different components of the electric field vector and hence determine the direction of the field. So now, what if when two electrically charged particles in empty space interact, how does each one know the other is there? Let us now define the concept of an electric field. So take a look at this figure. If you throw a ball upward, it follows a curved path due to the interaction between the centers of gravity of the ball and the earth. The centers of gravity are far apart, so this is considered as action at a distance. The concept of a force field explains how Earth can exert a force on things without touching them. The ball is in contact with the field all the time. Now, the concept of an electric field is a force field that surrounds an electric charge or group of charges. A gravitational force holds a satellite in orbit about a planet, and an electrical force holds an electron in orbit about a proton. The force that one electric charge exerts on another is the interaction between one charge and the electric field of the other. The question now is, how can you determine the magnitude and direction of an electric field? An electric field has both magnitude and direction. The magnitude can be measured by its effect on charges located in this field. So just imagine a small positive test charge placed in an electric field. Okay, so let's draw some test charge here, color blue. Okay, small test charge. So if we place a test charge here, this point, um, the force here is strong or greatest, meaning the field here is strongest. While if you place the test charge here, this part, the force here is weak, meaning the field here is small. So the direction of an electric field at any point, by convention, is the direction of the electric force on a small positive test charge. So if the charge that sets up the field is positive, just like this, just like this, the field points away from that charge. What if the charge is negative? The field points toward the charge. So since the electric field has both magnitude and direction, meaning it is a vector quantity, it can be represented by vectors. A negatively charged particle is surrounded by vectors that points toward that particle, as shown at this figure. So a positive charge has a vector that points away from that charge. So, meaning the magnitude of the field is indicated by the vector length. So, as you can see here, the arrows here are much longer compared to the arrows here. So this only means that the field is stronger compared at this part. Okay, so for an isolated charge, the lines extends to infinity. So what if we have two charges? Okay, two charges, or specifically we have two opposite charges. So our electric field lines looks like this. The line emanates from a positive charge, meaning it points out away from the charge towards the negative and terminate on a negative charge. And if you have a capacitor plate, the field lines are evenly spaced between two oppositely charged capacitor plates. So that is for the electric field lines. We already discussed the concepts about the electric field and the electric field lines. Now for the electric shielding, the concept of the electric shielding is if the charge on a conductor is not moving, the electric field inside the conductor is exactly zero. So when a car is struck by lightning, the occupant inside the car is completely safe. The electrons that shower down upon the car are mutually repelled and spread over the outer metal surface, and it discharges when additional sparks jumps to the ground. So the electric field inside that car practically cancel to zero. Now let us discuss the application of electric shielding, or the electric field inside the conductor. Consider a charged metal sphere, and because of the repulsion, electrons spread as far as possible uniformly over the surface. A positive test charge located exactly in the middle of the sphere would feel no force. The net force on a test charge would be zero. Hence, the electric field is also zero. So the complete cancellation will occur anywhere inside the sphere. Now, if the conductor is not spherical, the charge distribution will not be uniform, but the electric field inside the conductor is still zero. If there were an electric field inside the conductor, then free electrons inside the conductor would be set in motion. They would move to establish equilibrium. That is, all the electrons produce a zero field inside the conductor. And since we discussed shielding, what if we want to shield gravity? Well, there is no way to shield gravity because gravity only attracts. Now, what if we want to shield an electric field? Shielding electric fields, however, is quite simple. You just have to surround yourself or whatever you wish to shield with a conducting surface. Put this surface in an electric field of whatever field strength. The free charges in the conducting surface will arrange on the surface of the conductor so that fields inside will cancel. So by relating the shielding, electric shielding at this figure, the metal-lined cover shields the internal electrical components from external electric fields, and the metal cover shields the cable. If you recall my question from the previous slide, when two electrically charged particles in empty space interact, how does each one know the other is there? We can begin to answer this question and at the same time reformulate the Coulomb's law in a very useful way by using the concept of the electric field. Let's consider this figure at A. So the mutual repulsion of two positively charged bodies, A and B. Suppose that B has charge of Q naught and let F naught be the electric force of A on B. One way to think about this force is as an action at a distance force. That is, as a force that acts across empty space without needing physical contact between A and B just like gravity. To visualize the repulsion with these two bodies, we first envision that body A, as a result of the charge that it carries, somehow modifies the properties of the space around it, which is the body B. Then body B, as a result of the charge that it carries, senses how space has been modified at its position. The response of body B is to experience the force F naught. Here, for B, let us consider removing the body B and label its former position as point P. We say that the charged body A produces or causes an electric field at point P and at all other points in the neighborhood as well. This electric field is present at P even if there is no charge at P. It is a consequence of the charge on the body A only. If a point charge Q naught is then placed at point P, it experiences the force F naught. Now for C, we take the point of view that this force exerted on Q naught by the field at point P, okay, as shown here. Thus, the electric field is the intermediary through which A communicates its presence to Q naught, because the point charge Q naught would experience a force at any point in the neighborhood of A. The electric field that A produces exists at all points in the region around A. Okay? But we can likewise say that the point charge Q naught produces an electric field in the space around it, and thus this electric field exerts the force F naught on body A. For each force, meaning the force of A on Q naught and the force of Q naught on A, one charge sets up an electric field that exerts a force on the second charge. We emphasize that this is an interaction between two charged bodies. A single charge produces an electric field in the surrounding space, but this electric field cannot exert a net force on the charge that created it. Take note that a body cannot exert a net force on itself. Well, if this was not true, you would be able to lift yourself to the ceiling by pulling up on your belt. So now, we define the electric field E at a point as the electric force F naught experienced by a test charge Q naught at that point. And we can see this through this equation, meaning this is the force per unit area per unit charge exerted by A on a test charge at P. Okay? So, in SI units, the unit of force is 1 Newton and the unit of charge is 1 Coulomb. Hence, the unit of the electric field is 1 Newton per Coulomb. If we rearrange this equation, the force is just equal to the electric field produces at that point by charges other than Q naught multiplied by the charge Q naught. Okay, so this is the relationship of the electric force and the electric field. So here at this figure, we can say that the charge Q naught can be either positive or negative. If Q naught is positive, the force F naught experienced by the charge is in the same direction as E. While if Q naught is negative, then F naught and electric field are in opposite direction. Now let us consider the electric field of a point charge. If the source distribution is a point charge Q, it is easy to find the electric field that it produces. We call the location of the charge the source point, and we call the point P, where we are determining the field point. It is also useful to introduce a unit vector r hat, and that is the point that it points along the line from the source point to the field point as shown in this figure. Okay? So here, at each point P, the electric field set up by an isolated positive point charge Q points directly away from the charge in the same direction as the r hat or the unit vector. While in C, at each point P, the electric field set up by an isolated negative point charge Q points directly towards the charge in the opposite direction from the r hat. And you need to familiarize the direction, okay, in order to solve problems, and if you want to know the direction of your electric field. And this unit vector is equal to the displacement vector from the source point to the field point divided by the distance r. So the distance here is the absolute value of your displacement. So just remember this formula later. And using the unit vector, we can write a vector equation that gives both the magnitude and direction of the electric field. Here is the electric field due to a point charge. This is the electric constant that is equal to 9 times 10 to the 9 Newton meter squared per coulomb squared. This one is the point charge, the value of the point charge. R here is the distance from point charge to where field is measured. And r hat is the unit vector from point charge toward where field is measured. Our first problem. A point charge Q equals to negative 8 nanocoulomb is located at the origin. Find the electric field vector at the field point where x is 1.2 meters and y is negative 1.6 meters. So the given here is Q is equal to negative 8 nanocoulomb, and that is approximately negative 8 times 10 to the negative 9 coulomb. And the location is at the origin, where x is 0 and y is 0. And we need to find the electric field at x is equal to 1.2 meters and y is negative 1.6 meters. And to draw the free body diagram, this is the y-axis, and we need to draw the x-axis. Okay, so let's locate the points. And this one is the Q located at the origin. And if we set this as point 1, point 2, so around here, this is 1.2 meters. And since y is negative, so this is the negative 1.6. And the location of our field point is here. And since our charge is negative, so the electric field is going towards the point charge, okay? Going to the point charge. If this is positive, meaning it is going away, okay? So we need to recall the unit vector that we've discussed earlier. So unit vector is r hat over the displacement over the distance. So the displacement is given by this. So xi hat plus yj hat over r. And r here is the x squared plus y squared using the Pythagorean theorem. So our r hat is given by this. So our x is 1.2, our y is 1.6 over the square root of 1.2 squared plus negative 1.6 squared. And this is equal to 1.2 meters I hat plus negative 1.6 meters j hat over 2.0 meters. So our r hat is equal to 0.60 I hat minus 0.8 j hat. So for our electric field, this is given by 1 over 4 pi epsilon naught q over r squared r hat. So Again, this is a constant, and that is equal to 9 times 10 to the 9 Newton meter squared per coulomb squared. And our Q is negative 8 times 10 to the negative 9 coulomb over our R. Our R is 2 meters. And this is our R hat as what we have calculated here. So our electric field, so using the calculator, we can obtain these results. Negative 11 Newton per coulomb I hat plus 14 Newton per coulomb J hat. Okay, so we need to find the overall. This one is in component electric field. So we need to find the magnitude of our electric field, and this is given by this. Negative 11 Newton per coulomb squared plus 14 Newton per coulomb squared, and our electric field, the magnitude of our electric field is 17.8 Newton per coulomb. And for the direction, um, this is what you have learned from your vectors from the physics 1. So EY, the absolute value of EY over EX is 14 over 11. So the tangent inverse of this is equal to 51.8 degrees. And for our theta, this is equal. You just have to check the um, X and Y axis, so we can get the 128 degrees counterclockwise from the positive X axis. For the second problem, we are dealing with the superposition of electric field. Okay, so the problem is point charges Q1 that is equal to positive 12 nanocoulomb and Q2 is equal to negative 12 nanocoulomb are 0.1 meter apart. So such pairs of point charges with equal magnitude and opposite sign are called electric dipoles. Compute the electric field caused by Q1, the field caused by Q2, and the total field at point A. So this is the point A, at point B, and point C. Okay, so to start with the given, so our given is Q1, positive 12 nanocoulomb, and that is equal to 12 times 10 to the negative 9 coulomb. For Q2, we have negative 12 nanocoulomb, that is approximately negative 12 times 10 to the negative 9 coulomb. And our D is 0.1 meters. So we need to find EQ1, EQ2 at points A, B, C. So let's start with at point A. So E1A is equal to 1 over 4 pi epsilon naught Q1 over R squared, where R is 6 centimeter or 0.06 meters. Okay, so since we have absolute value here, meaning we are dealing with the magnitude only. So we will deal with the direction later. So here, Q1 and point A has a distance of 6 centimeter. So this 6 centimeter is equivalent to 0.06 meters. So E1A is equal to 9 times 10 to the 9 Newton meter squared per coulomb squared. And our Q1 is 12 times 10 to the negative 9 coulomb over 0.06 meter squared. And that is equal to 3 times 10 to the 4 Newton per coulomb. So for the E2A, meaning this is the charge to 9 times 10 to the 9 Newton meter per coulomb squared times 12 times 10 to the negative 9, though this is negative, so since again we have absolute value, so this becomes positive, and the distance is 0.04 meter squared. So that is equivalent to 6.8 times 10 to the 4 Newton per coulomb. So again, we will deal with the direction later. So let's just deal with the magnitude. For at point B, so this is the point B, So E1B is 9 times 10 to the 9, 12 times 10 to the negative 9 coulomb per, the distance is 4.04 meters, and that is equal to 6.8 times 10 to the 4 Newton per coulomb. For E2B, the distance between them, B here and here, is 4 plus 6 plus 4. This is 14 or 0.14 meters squared. And that is equal to 5,510 Newton per coulomb, or 0.55 times 10 to the 4 Newton per coulomb. So here at point C, our E1C is, this is C. The distance here is 13 centimeter. So 12 times 10 to the negative 9.13 meters squared, and that is equal to 6.39 times 10 to the 3 Newton per coulomb. And for the E2C, we also have again 13 cm. So this is the absolute value of negative 12 times 10 to the negative 9 coulomb over 0.13 meter squared. This is equal again to 6.39 times 10 to the 3 Newton per coulomb. Now, let us deal with the directions of the electric field. Since we've already obtained the magnitude of our electric field, so just remember that the electric field of a positive charge is going away from that charge, and the electric field of a negative charge is going towards that charge. So at point A here, so at point A, I just draw in this part. So A here, this one is the negative and this one is the positive Q1, this is the Q2. So since we have a positive Q1, the electric field at point A goes to the right. It goes away from the charge. While for the Q2, it goes towards, meaning the E1A and E2A are both directed to the right, meaning it goes to the positive x direction. So EA here is E1A I hat plus E2A I hat, since these are both in x direction. So 3 times 10 to the 4 Newton per coulomb I hat plus 6.8 times 10 to the 4 Newton per coulomb I hat is equivalent to 9.8 times 10 to the 4 Newton per coulomb I hat, meaning these are in x direction. So let's consider at B. So this is our B here. So if we have positive charge here, this one, our B is in the left. Okay, so the electric field, due to our charge 1, the electric field is going away. So our E1 goes to the negative x. While our E2, since it goes towards our negative Q2, so the direction of our E2 is going to the right. Meaning E1B is directed to the left and E2B is directed to the right. So EB, since it's going to the left, we have negative E1BI plus E2BI hat. And we can have this negative 6.8 times 10 to the 4 Newton per coulomb plus 0.55 times 10 to the 4 Newton per coulomb. And that is equal to negative 6.2 times 10 to the 4 Newton per coulomb I hat. So for the electric field at point C, here, since the point C is located at this point, okay, and we have angles, meaning we have a x and y components, okay. So let's draw. This one is the y component of E1y, E1y, E1cy, and this one is E1cx, and this one is the E2 for the charge 2, and this one is the what they call this, the y component of the charge. Okay, so here, if we can say, or we can see here, that by symmetry, the E1CY and E2CY are the same but opposite. Okay, so let's start by symmetry concept. So E1CX is equivalent to E2CX, and that is E1C cosine alpha. So recall the cosine. Cosine is the adjacent side over the hypotenuse. So the adjacent side, and this is equal to 5 since the total here is 10 cm. So we have 5 cm here, 5, and the hypotenuse is 13. So just like this, so we have 5 sides here, and this one, the hypotenuse, is 13. So the cosine alpha is equal to 5 over 13. So rewriting E1CX plus E2CX is equivalent to 6.39 times 10 to the 3 Newton per Coulomb times 5 over 13. That is equal to 2.46 times 3 Newton per Coulomb. Again, by symmetry, we can say that E1CY is equivalent to negative E2CY. So 6.39 times 10 to the 3 Newton per Coulomb. Sine alpha is, where sine alpha is opposite over hypotenuse. So sine alpha is 12 over 13. So where the 12 here is the opposite side. So we need to recall x squared plus y squared is equal to r squared. So to have the y side, so y squared is equal to r squared over x minus x squared. So you just move x squared to this side, so it becomes negative. And y is equivalent to the square root of r squared minus x squared. That's why we obtain the 13 squared minus 5 squared, and that is equal to 12. See the 12 here. Now let's proceed. E1CY is equivalent to negative E2CY, and that is equal to 6.39 times 3 Newton per Coulomb. 12 over 13 is equal to 5.9 times 10 to the 3 Newton per Coulomb. And EC is equal to E1CY plus negative E2CY. So that is 0. So meaning we have no y component because it cancels out. And for EC, the only component is CX. So our E1CX plus E2CX is 2.46 times 10 to the 3 Newton per Coulomb plus 2.46 times 10 to the 3 Newton per Coulomb, and that is equal to 4.9 times 10 to the 3 Newton per Coulomb. I hat. So this is the direction. That is all for our lecture 1. So thank you again for listening and for bearing with me. And I hope that you learned something for the electric charge, electric field, the Coulomb's law. So you just need to practice more on solving the problems. And again, see you for the next topic, which is the electric potential. Thank you again.